All right, so in this video, we're going to start to look at non-equilibrium forces problems. And starting here with this old quiz here. And let's see what we got here for this first one. I'm probably going to draw this on a page below just because there's not a lot of room here. So I recommend that you do the same. Pause the video, get a separate sheet of paper, because if you're working just off this piece of paper, it's not going to work out very well for you. It says, number one says, while fishing you catch a tire. If the mass of the tire is 12 kilograms and you yank the trophy catch out of the water vertically with an acceleration of 3 meters per second squared, then the magnitude of the tension in the fishing line is what? So let's go ahead and draw this. This will be question number one. We have a person sitting here fishing. I'm going to go ahead and give him a fishing hat. And let's see here. Okay. Maybe they're fishing at the end of a pier. We have some water here. And a fishing line. And a tire. Okay, so we're going to go ahead and draw a free body diagram here in a second, but what is our object of interest? And I want to say it's going to be the tire. I'll draw a dot on the tire. Our forces here, there are two, right? It's a 12 kilogram tire with two forces on it, so I'll just go ahead and make a note of the 12 kilograms. I'll write that right here on the side of the tire. And what are the two forces? Think about it for a second. You should say force gravity. And you should say tension. Now, in previous problems, our forces would be drawn equal here. But since we have accelerated motion, I am going to draw tension as being larger. And I think because they tell us there is a net acceleration, and I can just write this right off to the side, of 3 meters per second squared, upward, right? That there is some net acceleration in this direction. Okay. What else do we know about this problem? I think that's it. Yeah. Okay, and they want us to find what is the magnitude of the tension in the fishing line. Okay, so what is T? So we're going to work these problems just like we did before. Start by a drawing, a free body diagram. We did that. And then pick a direction to work in. Clearly, we don't have to worry about the X direction. But in the Y direction, we should assign a coordinate axis system. We'll call up positive Y. We'll call down negative Y. We'll then go ahead and sum our forces in the Y direction. So we say sigma Fy equals MAY. And we know that tension is pointed up, so it'll be positive. We know that force gravity is pointed down because it's negative, or so it is negative. And the reason we know that is based on this coordinate axis that we assigned, right? We said down is negative Y. We said up is positive Y. All right. Over here, we're going to go ahead and apply the mass of the tire, which is 12 kilograms. And this is the net acceleration the tire undergoes, which is going to be that positive 3 meters per second squared. So far, so good. We don't know tension, so we'll just rewrite that for the next line. We know FG is always mg. All right. So notice that even though the tire is accelerating at +3, right, upwards, that force gravity is about its weight, and the weight of the tire itself uses its mass times 9.81. So I just want to point that out because sometimes kids have confused those two accelerations and they're not the same. 12 times 3 is 36, so this is going to be 36 newtons over here. Because the mass times an acceleration is a force, so F equals ma. So anyways, so units should be in newtons. Let's go ahead and apply our mass or sub in our mass over here. That is 12 sub in baby G, which is 9.81. Now you might say, well, it's pointed down, so do we call it negative? No. The negative sign was already applied right here, right? We put the negative sign right there in the problem on force gravity. So force gravity is, we already know it's negative. Okay. So do not apply your negative sign twice. If you do, you'll get it wrong. Go ahead and rewrite 36 newtons. 12 times 9.81 is a little under 120. Let's go ahead and multiply that. I'm getting about 117.72. Once again in newtons. All right. Signs are super important. We'll go ahead and add. We got to simplify this and get t alone, so we'll add 117 to both sides. These two will cancel. Can I do that in my head? I don't know. That looks kind of tough. So what would that be? 36 plus 117. That'd be plus 30 is 47, plus 6 more is 53, so 153.72. Sounds right. You can double check with your calculator if you like. All right, that's all there is to it. So a small difference in how we do these problems, right? Just very similar, but the small difference being that the acceleration is no longer 0. All right, so now we're going to look at problem 2 here, which involves a pulley. As we can see, 2 blocks are connected with a string or rope or crates or something along those lines, and they're on top, or one is on top of the table, one is on the side of the table. I like to refer to these kind of problems that look like this as Atwood pulley problems. So if you want to write that down. That is what we're dealing with here. Okay, so it says, assuming there is no friction, find the acceleration of the 2-block system. So when the 2 blocks are connected like this, by a string, the acceleration of the block 10, or the 10 kilogram block, is the same as the 18 kilogram block. So what I'm saying here is the acceleration of both blocks together will be a certain value. And that is the same as if we just considered one block alone. And that's going to matter in this problem because we're going to introduce an idea here, which I think we may have talked about before in this class, and that's something called a system. A system is it's an analytical tool. Let me see, how do I want to write this? I'm just going to say it's an analytical tool that allows us to solve the problem. Now, it is an abstract idea, meaning, meaning that how you define the system can differ. You do not have to define, you want to define the system in the best way for the problem. A system can be something that's very large. It could be the universe. It could be something that's very small. It could just be one of these blocks. In an Atwood-Pulley problem, you can solve this different ways based on how you define the system. When I define a system, I like to draw a yellow dotted line around the system. So that's what I'm doing right now. So feel free to draw a dotted line around the two blocks. Notice I'm including the pulley. I'm including the a little bit of the table, I guess. Lab table or desk or whatever these two blocks are on. All right. And yeah, and then so this is how I'm calling this right here the system. Now this is an idea that's important in all science classes, in biology and in chemistry as well. And it's really what we're studying. So the system is what we're working with and studying. So when things are inside the system, we like to refer to them as internal. I'll just write. So inside that yellow box. And if it's outside the yellow box, we'll refer to it as external. Now we've used that term before in this class. If you think back to Newton's first law, the law of inertia, an object in motion stays in motion, an object at rest stays at rest unless acted upon by an external force. And it was kind of odd, I mean, you could understand the law completely without seeing or hearing the word external in there. So why is external in there, right? And it gets at the idea of systems. If something is external, it's outside the system. And there's a difference between external and internal forces. And so you can see my screen recording there is popping up on the screen. I've been having some technical difficulties. I actually made this video earlier, but not too successfully. And the sound wasn't working, so I'm making it again much later in the evening now. So, oh well. All right, so you have this idea of internal and external, and this idea of systems. All right. Then there's also this idea of an ideal pulley. So pulleys that don't have friction, right? We already said there's no friction for this problem. So if there's no friction, we know that mu, I'm just going to write it up here, is equal to 0. Now, you can do an Atwood-Pulley problem with friction. This table very well could have friction. It just doesn't for this problem because we're trying to make the problem a little bit easier. But we're assuming that the pulley here is ideal. And so this is the pulley right here in blue. And you can see the string is draped over it. So when we assume that the pulley has no friction, we call that an ideal pulley. And this is something that will show up sometimes in a problem. If something's ideal, it is under the best circumstances, and it minimizes things like friction. So I'll just write no friction from the pulley. Now in real life, you would have friction from the pulley. And you would go out of your way to minimize that, but we're assuming for this problem that it's an ideal pulley. Okay. So in this problem, we'll look at what's going on with an Atwood pulley problem, but in regards to the idea of a system. So an analytical tool that allows us to solve the problem. How the thing to understand about systems, I want to write a little bit more, is that how you define the system. Let me write this maybe. Just draw an arrow here. How you define the system. This is systems kind of continued. Oops. Ugh. Does not affect the problem. The system affects how you solve the problem. All right, this is a key idea. So what I'm trying to say here is that how you define the system, right, doesn't change anything. So meaning if you are looking at these blocks and you define the system to be 2 blocks and I define the system to be just 1 block, the blocks don't care what we think about about the problem, right? Meaning the blocks on the table are going to slide however they're going to slide, regardless of how, if you do the problem one way and I do the problem the other way. So the system doesn't matter what you call the system. It doesn't change what really happens, right, when you attach 2 blocks to a pulley. That is very key to understanding this idea. If you understand that, then you're halfway there to understanding this concept, easily halfway, more than halfway. So the system instead affects how you solve the problem. So if I define the problem as 2 blocks or 1 block and you define it as 2 blocks, we are solving the problem differently. And that is really the main idea here. Now, it also changes what we consider to be external and internal, obviously. And so that's why it changes how we solve the problem. Yeah, so that's kind of the idea here. The system can be as large as you want, as small as you want, and that's what's tough. And that's students struggle with that, right? Because they're like, well, how large do I make it? And the answer is you do it appropriately for the problem and you define it appropriately for the problem and you do it so it makes your life easy. So you try to do it in a way that will help you solve the problem efficiently. It doesn't matter. You don't want to just make it as large as you can or as small as you can. You want to do it correctly for the problem. So it takes a little bit of practice. And by doing these, you'll start to recognize what is the best way to do these problems. So a useful idea, whether it's physics, bio, or chemistry, maybe in chemistry, if you had a beaker that is the system and anything external to the system is in the environment, and you can talk about the heat flow into the environment from the beaker or from the environment into the beaker, and you can talk about whether it's exothermic or an endothermic reaction, and so this shows up in chemistry as well. All right, but let's look at it in regards to this problem right here, which is an Atwood pulley problem. So I'm going to go ahead and redraw because I want a little bit more or a lot more room, and I hate being confined to a small space to write. Okay. Okay, so what we have here is a table, obviously. And you can already tell this problem is different because one block is on the table and the other one is on the side of the table. You can also tell the problem is different because there's two blocks. And a good question is, well, which one should we free body diagram, right? And the answer is both. So we're going to go ahead and start free body diagramming. Just working on my cross hatching here. We're going to start by free body diagramming both of these. And we might as well label them too. Pulley drawing's kind of rough. Okay. Let's put a dot on this one up here. And this is going to be the 10 kilogram block. I'm just going to put a little note there so I don't forget. And this is going to be the 18 kilogram block on the side. Okay. Now, on this 10 kilogram block, we want to do a free body diagram. Let's go ahead and draw those forces. Obviously, a force gravity. I'm going to call it FG10 just because I have two blocks and I don't want to confuse the force gravities for each one. There's going to be a normal force that's going to be opposing this. I'll call that just Fn. And then finally, there's going to be a tension force to the right because the block is going to be pulled by this string. Remember, ropes don't push. They just pull objects. So, all right. So I think that's good. I think that's all we have there. On this block over here on the right, we are going to have tension once again, but this time pulling up. We're going to have another force gravity. I'm going to draw this one a little longer. This is going to be FG18. And that's it. Notice there's no frictional force. Obviously on this one's not contacting the table, but especially on this one right here, because mu is 0. There could have been friction, but there isn't for this problem. Just like there's no friction from our pulley. Okay, so what we're gonna do here to solve this is we are going to call once again the system is going to be both blocks. I'm trying to draw this yellow dotted line. Let me make this a little bit smaller. And I'm going to get a little bit of table in my system, and that's fine. And so the system is both blocks together. It is not just one block. And so let's go ahead and see. Redraw that. Trying to make this look better. We're gonna solve this problem by talking about the fact that these blocks, we expect them to slide off the table because we attached a heavier block on the bottom and a lighter block on top. So how quickly though is it going to accelerate off the table? And so that's what we're going to find out. But a trick to solve this that we like to use with Atwood pulley problems is we are going to call this direction right positive x when it's on the table and down positive x when it's on the side of the table. So once again, the way I labeled that, right, it's kind of funky looking, right, because it goes right, then down. Then I draw my arrow. So what we're saying is that these two objects are going to slide to the right on top of the table and down when they're on the side of the table. And so what we have is just one direction for this. For really, it's just one object, right? We're since this is the system, we're kind of, even though we drew a free body diagram for two separate objects, we're really just considering this moving as one object. We said the accelerations are going to be the same because it's attached via a string. And that's important to remember. And I'll bring, maybe I'll write that down right now. So I'm just writing here, the acceleration of both blocks is the same because they are attached by a rope or string. So that's important to realize when you're working with these Atwood-Pulley problems, is that that's true. Okay. All right, so should you write that down? Probably, because I could see that being something that that you would forget at on another problem. All right, so anyways, so let's go ahead and solve. Right, this is similar to other problems. We draw, we free body diagram, we sum our forces in the x direction and the y direction. But here, we're only going to sum our forces in the x direction, and I think it's going to be enough. Now, it is going to be this funky x direction where it's going to depend which block is where to know what the x direction is. So let's go ahead and write it out, and I'll kind of point out as we go here what's going on. So I guess if you want to write x direction, this is what we're working with. And I'm just going to write system is both blocks, just so we know that this calculation goes with that. Sigma fx is equal to max. So there's Newton's second law in the x direction. We can go ahead and plug in our x forces. Because, before I do that, because the system is both blocks, the mass here is going to be both blocks. And that's because that's the system, right? Because the system is both blocks, the mass is both blocks. And that is really important to understand and a source of error if you forget it. All right, so let's go up to the first block. Are there any x forces? Well, this block is on top of the table. X forces then are directed right or left, right? Because this green arrow tells me when it's on top of the table, positive x is to the right. So right here, I see tension is a positive x force. So I'm going to go ahead and write that in. All right, and that's for the first block, the 10 block. The 18 block, the heavier block, has two positive x forces. Because of this green arrow, when the block is on the side of the table, down is positive x. So once again, when it's on the top of the table, right is positive x, according to this arrow. But when it's on the side of the table, down is positive x. And furthermore, when it's on the side of the table, then up is negative x. So we are saying then FG18 is a positive x force and tension is a negative x force. All right. And notice I use the same t variable there. I'm gonna go back up and show you that. You can see it right there in the problem. This is going to be both masses, so we're saying 10 kilograms plus 18 kilograms. Obviously 28, but I wanted to write it out. We want to solve for acceleration in the x direction. But what I'm saying here is these two t's, these two tensions, right, that are on these two blocks that are separated by this string are equal and opposite and are identical in magnitude. So they both have the same value. So they're equal and opposite, and so they're a Newton's third law pair. the two tension forces that occur on different objects. For Newton's third law of pair, the forces should always occur on different objects. All right, so down here we can then cancel these two t's, right? Because t minus t is just 0. FG18 is obviously going to be mg, but what might not be obvious is it is just the mass of the 18 block times baby g. Also, baby g isn't negative because we already applied the sign on FG18 up above. It's positive, represented by the plus sign right next to it. So I do not reapply a sign here on g. And FG18 is only, even though the system is both blocks, FG18 is only the weight of the 18 block. So, because look at it, right? It doesn't care what's going on the 10 block. It doesn't care there's another block there. The weight of that block, FG, is 18 kilograms times baby g. So we have to remember that down here. So this is tricky, right? Because one mass on the left side is 18, and the mass on the right side is 10 plus 18. So it's already starting to get a little difficult. Those little mistakes, if you make them, can make or break the problem. So let's go ahead and plug in some numbers on the left. So we know this is 18 kilograms. We know this is baby g, which is 9.81. All right. And it looks like we're going to need a calculator here. All right. So 18 times 9.81 is 176.58. And that's going to be newtons, kilograms times meters per second squared. I mean, that is a mass times an acceleration, so F equals ma, so we are in newtons, assuming we started with kilograms and meters per second squared. And over here, we still have 28 kilograms. So all we have to do is a little division. And we should be able to get our answer in meters per second squared, which is 6.306. So 28s cancel, kgs cancel. So what I'm saying here is on this side, it's about 6.31 meters per second squared. Notice the acceleration is positive. This is in the positive x direction, which is to the right when it's on top of the table and down when it's on the side of the table. And think about what it's saying, right? Does this answer make sense? Well, what it's saying is both of these blocks, right, or a single one of these blocks, either way, are going to accelerate at 6.31 meters per second squared. So if we go back up and look, when this block, for instance, let's just look at this 18 block. When it's on the side of the table, it's going to fall, right? Which we thought was the case because it's a heavier block attached to a lighter block. The lighter block can't really hold it up, especially since it doesn't have friction there to help it. So it's on a frictionless table. When this accelerates to the ground, it accelerates at 6.31 meters per second squared, which is slower than an object in free fall, right? It's slower than 9.81 meters per second squared. So why is that? Because it is being held up by the string, right? This string, this tension force is holding it up and causing it to accelerate a little bit slower than it would if the string wasn't there, if it was just dropped and there wasn't this 10 kilogram mass on the other side of that string. Okay, so that's our answer. And that's how it's done. So this is called an Atwood pulley problem. You can see with the system as both blocks. Now, they did not, or I am not going to show you how to calculate that focusing on one block because I find that it's confusing. And I find that this way of doing things is better. The students like it more. It's just a better way to do the problem. But you're free to try resolving this with one block at a time. It is tricky, but it can be done. So a lot of times I like to ask a bonus question here, or a second question really, for problem 2. So we'll call this question 2b. And I know it's not on this quiz, but if I was writing this as a test, this question would be on here. What is the magnitude of the tension in the string? All right. So, okay. So I like to ask this question. Here's a lot of times what happens. So the student will go, okay, I can solve for that. There was tension in the problem. I remember it was there. So they will do this. They will write sigma fx equals max. And let's be clear. Let me look at the picture here and show you. So I'm saying solve for t, right? It's on both blocks. But they will do the problem correctly in the first part, get 6.31. Then they'll be on this problem, and they will rewrite it like before, right? They'll be like, okay, some of the forces in the x direction on the first block, we had just tension pulling to the right. So that was the only positive x force because it's on top of the table. And when you're on top of the table, right is the positive x direction. Then here they'd be like, okay, on the side of the table, FG18 is the positive x direction, and tension is on this block is a negative x force. So we're going to subtract that. So anyways, you get this, which we already did before. We just did this. The mass was both blocks, which was 28, right? It's 10 plus 18, so 28 kilograms. And the acceleration we just solved for is 6.31 meters per second squared. Remember, this is the acceleration of one block, the 10 block, the 18 block, or it's the acceleration of both blocks together. Any way you look at it, it is 6.31 meters per second squared. So then this happens, right? So they think they're going to solve for tension, and then that cancels away. All right. So that's a huge problem. We're not going to be able to solve for tension if it doesn't stay in the problem. So how do we deal with this, right? So what we're going to do to fix this, right, is work with redefine the system for this problem. So to solve this, we're going to call the system one of the blocks only. Now, which block should we work with? Should we work with just this one to find the tension, or just this one? And my answer is it doesn't matter. You can work with either block. But it is going to change how you solve the problem, right? It's going to be slightly different. So I will make the choice here and say let's work with just this block as the system. And so this is block 10. So I'm going to go ahead and write that down right here. So system is equals block 10 only. All right, and we're going to keep the direction the same, that funky x direction of right is positive x when it's on the table and down is positive x when it's on the side of the table. So we're going to keep that the same. So let's work in the x direction just like we did before. Draw that right there. So we'll say sigma fx equals max. All right. Block 10, right, is what we're working with. That's what we said. So if we look at just block 10, we can see the only X force on it is tension, because on top of the table, right is positive X. So, and it's in the positive direction. So I'm going to go ahead and write that down. Whoops. Okay. I have T, and I'm going to set it equal to the mass. Now, this is only block 10. And that should make sense because the system is block 10 only, right? And so the mass reflects that. All right, so let's go ahead and plug that in. So we're just going to have a 10 right there. Now the acceleration is the same as the 2-block system because it doesn't matter if we look at one block at a time or both blocks. The acceleration, because they're connected with a string, is going to be the same for both blocks. And that's going to be 6.31 meters per second squared. We can do the math in our head. 10 times 6.31. Just move your decimal over once. We're going to get 63.1 newtons. And there it is. Now, you might be sitting there saying, well, okay, what if you would have picked the system is the 18 kilogram block? Right? What would have happened? Well, what we're saying is you should have got the same exact answer, right? Let's see what happens. Let's see if that's true. Sigma Fx equals Max. Once again, working in the new X direction. Block 18 is on the side of the table. So FG18 is positive X because down is positive X on the side of the table. And T is negative X on the side of the table, or up is negative X on the side of the table. So we have FG18 minus T. All right, so let's write that in. Okay, mass, once again, right? Like I just said, only 18 kilograms. Because of how we define the system, right? It was block 18 only. Okay. So we're saying 18 kilograms times, what was the acceleration? 6.31? Yeah. All right. And so, okay, this one's looks like it's going to be a little bit more work. FG18 is going to be mass 18, right? 18 kilograms times baby G. It's the weight of the 18 block only. Notice that this one's 9.81 for acceleration. This one's 6.31. This is the net acceleration over here in yellow. And this is the Earth's gravitational field. They are different. And that is why, baby G is used for calculating weight. AX is the net acceleration of the blocks. Okay, so they're completely different. All right, so let's go ahead and multiply that. So 9.81 times 18, that's that 176. We already did that earlier. 0.5. God, I can't read my calculator. Is that 0.58? Yeah. Okay, so, and this is obviously going to be minus T is equal to 18 kilograms times 6.31. All right, I'm writing probably more steps than I need. So when we crunch 18 times 9.81, we get that minus T is equal, what's 18 times 6.31? That is 113.58. All right. Okay, so now we just do a math move here or two, and we got the answer. So we'll notice the negative sign hanging out here next to the T. That is important, right? A lot of times, let's finish this, and then I'll mention something about the sign. I guess what I want to say is this. A lot of times our final answer is going to be just a magnitude. It's going to be amount. You have to apply the signs. So let's go ahead and kick 176 over to the other side. All right, cancel, cancel. And we're left with negative t is equal to, now, what is this? The 0.58s are going to cancel. So we have 76 minus 13. 70 minus 10 is 60. 6 minus 3 is 3, 63. So 63, it's negative too because the negative is larger. Negative 63.0 newtons. Negative signs on both sides. Multiply both sides by -1. Divide both sides by -1. Whatever you want to do, they're going to cancel. So we can see here that tension is equal to 63.0 newtons by looking at just the 18 block only. Is it the same as looking at the 10 block only? Yeah. Well, you might say, well, it's slightly different. It's 63.1. That difference is insignificant. It's that's based on an error calculating, just error propagating through the problem because we calculated differently. So you have to know based on the problem whether or not that slight difference in numbers is error from the problem or if you did it wrong. If we were getting like 66 or 67 for one and 63 for the other, that's significant, a significant amount of error. I would do that problem over. If you're getting 0.1 or 0.2, you're all right. If you're getting like 10 or 20, obviously do the problem over. But even like 3 or 4 Newton difference, you should be doing the problem over because that's not close enough. So so here you have it, right? Didn't matter which system you chose. You could solve for the tension and get the same exact answer. Okay, so long story short then, with an Atwood-Pulley problem, you have this idea of systems that's super important. It's an analytical tool for solving the problem. It does not affect the blocks. I don't care how you solve the problem or somebody else solves it differently. There's only one correct answer, and that is what the universe does. But the system changes how you solve it. It is an analytical tool that helps you to interpret the problem, and it can make your life easier if you know how to define the system, which is an abstract idea, and students have problems with that, so it's not easy. We also did the unique thing of calling right and down positive x, right? And that's weird, and that's why we call this an Atwood-Pulley problem. So we went ahead and solved for the acceleration with using the entire system, working with this weird x direction, and both blocks as the system. So we saw that the mass here was both masses added together. We solved and got 6.31 meters per second squared. I then asked a bonus question, which I usually ask on these tests, and what is the magnitude of the tension in the string? We could not use the system with both blocks because the t's canceled away. So we had to pick one block only, whether it was 10 or 18. Whichever we picked, we should have got the same answer of 63.1 newtons. We still use the same direction for the x direction, and it didn't matter, and it worked out. Slight difference, but that's negligible. All right, so that's it. Hopefully this is making sense. I know there's one more problem on this practice test, and I think I'm going to make another part to the video and save that for next time. So that's it. Take care.